All right, we know what a vector is, so now we need to know how to name a vector, okay? But before we even know how to name a vector, we need to know, what does a vector even look like, okay? So remember, vectors are made of two things: a magnitude, in other words, how big it is, and a direction. In other words, where is it pointing, okay? So there's really only one thing that has both of those aspects, right? And that is an arrow. Okay, so if you guys can turn to the slide that says vector notation, we're going to explore this. So a vector's length, okay, describes its magnitude or how big it is, right? And the vector's arrow tells you which direction it's going in, okay? So we always want to set a context for a vector, right? And so the context is usually just the normal Cartesian plane, a y-axis and an x-axis, right? Okay. So now we have this vector in space, okay? But we can't really do any math with it yet because it doesn't have a name, all right? We don't have any way of expressing it. So let's figure out how to express it, okay? Well, the first thing that we look at is we notice that there is some part of this arrow that points in the x direction and some part of this arrow that points in the y direction, right? It points into both. It's not totally straight and it's not totally up. There's some part that points x and there's some part that points y, okay? And so we want to name those. We want to give those guys a name, and we're going to call them the components of the vector. And so we say that this vector here, we'll call it v for vector. And vectors always have a little arrow over the top to represent how big it is, to represent that it's a vector, because the little arrow means vector, okay? So now it has, this vector v has a x component, which means some part of it that points in the x direction. We're going to call that vx, right? And then it has some y component, which means some part of it that points in the y direction. Okay? So this means then we could very, very easily describe this or name this vector by saying that a vector is something that has some parts in the x direction, right? And to say it's in the x direction, we put a little I hat here. I hat means we're pointing in the x direction, okay? So these guys are called unit vectors if you haven't seen them before, okay? And then we have another part over here in the y direction, okay? And we say that the y direction is j hat, okay? So I hat means the x component pointing in the x direction, and the j hat means the y component pointing in the y direction, okay? And if this were a three-dimensional vector, then we would say plus vz in the k direction. So k is the unit vector for z, for the pointing in the z direction, okay? So now we have a name, okay? We have a name for this vector. It's vxi plus vyj plus vzk, and this makes it much easier for us to start doing mathematics with this vector so that we can add them and solve for different components and things like that, okay? So just to be totally clear, let's say vy was equal to 5, okay? And let's say that vx was equal to, I don't know, 3, all right? So that would mean that our vector would be 3i plus 5j. Okay? All right. Don't worry about the lengths. I know I made 3 smaller than 5, but 3 is actually longer. Don't worry about it. If that's 3, you put 3 in for I. If the y component's 5, you put 5 in for j. Okay? So, guys, now we have a name for vectors. We have a way of expressing them. We have a notation. Okay? Now, this begs the question. If you guys could advance to the next slide. The question is, how can we find out the 2 things that are most important about a vector, right? And those 2 things are its magnitude, all right, which usually, honestly, is just written as the v without the little arrow over it, okay? So how do we find the magnitude of a vector, and how do we find its direction, right? In other words, the angle at which it points, okay? Those are the 2 things that we care about, okay? How can we solve for them? All right. Well, this is where we take a moment to notice that these components and the vector itself forms a beautiful little right triangle. And you guys know so much about the math of right triangles already, right? we know SOHCAHTOA, we know Pythagorean theorem, which means we can solve for everything we want to know about vectors by knowing these simple properties of a right triangle. So for example, if we have a right triangle that's C, A, and B, how do we find the hypotenuse? In other words, the magnitude, right? Well, the hypotenuse is always just C squared equals A squared plus B squared. So the magnitude of the hypotenuse is just the square root of A squared plus B squared. Okay? Piece of cake, super, super easy. That means that the magnitude of a vector is always just equal to its x component squared, right, plus the y component squared, square root of the whole thing. Okay? Easy breezy, totally plug and chug. We can always find the magnitude of a vector simply by taking the components, squaring them, adding them, taking the square root, just like Pythagorean's theorem. Okay? And what about the direction of the vector, right? We need to know what direction this vector is pointing. Well, it's pointing at some angle from the x-axis, as we can see from here, right? And we also know from SOHCAHTOA that tan theta is equal to opposite over adjacent, right? But in this case, opposite is just Vy, right? So that's really Vy over adjacent, which is Vx, right? So tan theta is Vy over Vx. We take the inverse tan to solve for the theta angle, and we see that the angle is always going to be inverse tan of Vy over Vx. Okay? Piece of cake. So just to be clear, what we've done here is we said if we have the two components of a vector, how do we find the magnitude and how do we find the direction? Okay? If you advance to the next slide, there's also another question of, let's suppose you have the magnitude and the direction. Okay? How then can we solve for the components specifically? Okay? How can we get Vy and Vx from the magnitude and the direction of the vector? That'll be in the next video, and I'll see you guys there.